Hello students, our today's chapter is carboxylic acid and its derivatives. Previously we have covered some reactions of this topic in alcohols and we have also covered some reactions in carbonyl compounds. So that reactions which are already covered, I'll quickly brief them, but no need to write them again here because already covered. In practice you can try in your rough notebook. Now starting with the initial part, which is IUPAC nomenclature. Now here in detail you have already covered every functional group in actual nomenclature which was taught to you earlier. Now here only few examples and general idea about the nomenclature of carboxylic acid. IUPAC, in IUPAC prefix is carboxy for COOH group and suffix is oic acid. Oic acid, when it is attached to acyclic carbon chain, then we name it alkanoic acid. Oic acid is suffix. Second suffix is carboxylic acid. When COOH group is directly attached to ring, then we use the term ring, that is cycloalkane carboxylic acid. This is general way. When COOH is attached to ring, then we use its second suffix, which is carboxylic acid. That means its carbon is not counted in the ring, but in acyclic chain we count its carbon. That's why we use oic acid. We understand it by example. First example, in this case, carbon chain and carboxylic group. Now functional group is present, so we select longest chain and give first number to carbon containing functional group, which is carboxylic acid. 1, 2, 3, 4, 5. If you select that chain 1, 2, 3, 4, 5, 6, it becomes 6, but we will select which one? That parent chain which contains functional group and which is carbon containing functional group. Then we give number 1 to that functional group. There are rules for that. I hope you remember that rules. I am quickly going as per the example. Now here at second position, ethyl group. At second ethyl, 2 ethyl, parent chain contains 5 carbon, pentane, oic acid. No need to mention 1 oic acid. Why? Because carboxylic group carbon will get first number in open chain structure. Second example, in case of ring. In case of ring, the carbon of the ring which is attached to carboxylic group, it becomes 1 number. Now there are two possibilities, either anti-clockwise or clockwise. If we go anti-clockwise, multiple bond gets second number. If we go clockwise, substituent, because if you remember halogens are always treated as substituents, it gets second number. Now which is preferred? Multiple bond will be preferred over substituent. 2, 3, 4, 5. Then it is 5 bromo at fifth position substituent. Then cyclopent at second position double bond, pent 2 ene, and then carboxylic acid. Here we are using not oic acid. Why? Because the carbon of carboxylic is not counted. That's why we use second suffix carboxylic acid, and here what is dot? It means cycloalkane carboxylic acid. Third example, a prominent example, that in this case also we use second type of suffix. Why? Because if we consider this carbon and this carbon, this COOH which is in the middle, it becomes a prefix. Therefore, in such cases where carboxylic group is 3 times or more, then we select the parent chain and these carboxylic groups will be attached to the parent chain, just like carboxylic acid we have done in example number 2. So here numbering will be from any of the side 1, 2, 3, because if we select them 1, 2, 3 carbons, on each carbon there is a functional group which is carboxylic group. Hence it will be propane, first, second, third. Propane 1, 2, 3. How many times? 3 times. Tricarboxylic acid. Because it is clearly possible that if we select this side chain or 3 carbon chain as the parent chain, with each carbon carboxylic group is attached, and then we use second type of suffix, or if it is coming 3 times or more, then we select carboxylic acid as the prefix. Example number 4th, important example, benzene carboxylic acid. In dot I have left it, you can write it benzene carboxylic acid, and the common name is benzoic acid, but this common name is IUPAC accepted also. So here benzoic acid is IUPAC accepted, or benzene carboxylic acid, more important is benzoic acid. Fifth, in example number 5th, carboxylic group is attached to side chain, that's why it is aliphatic carboxylic acid. Previous one was aromatic. Now in this case, numbering will start from carboxylic carbon which is in the side chain or open chain structure. 1, 2, 3. On third carbon there is a substituent now which is phenyl ring. 3 phenyl prop 2 ene. At second position double bond. 3 phenyl prop 2 ene. Then it is propanoic acid. Why? Because it is a substituent. Sorry, it is a side chain aliphatic to prop 2 ene oic acid, and here E of the ene is dropped. Why? Because it is followed by O. Therefore, in example number 5th, again listen, this carboxylic group is attached to side chain. It is aliphatic, that's why we will count its carbon 1, 2, 3. Then on third position ring becomes prefix 3 phenyl prop 2 in. Second position double bond 2 in oic acid. We will not use carboxylic acid. Why? Because carboxylic acid, when it is attached to directly ring structure, then we use benzene carboxylic acid, or as per the ring structure. Example number 6th. In 6th we have two carboxylic group. One is directly attached to 3-membered ring and second is attached to side chain CH2 then COOH. Now out of these two, only one will become in the parent chain, other has to be prefix. That is the use of carboxy. Now in that case, ring is of 3, 1, 2, 3, and side chain contains one carbon, and this one carbon then attached to COOH. Therefore we select this ring as a parent chain, and then this part CH2 with COH, it becomes a prefix. Therefore select the number 1 where carboxylic group is present, 1 number, then substituent will get second number, then third number. Now at second position we have a substituent which is methyl, and then COOH will name it as carboxy because it is now prefix. At second position in the parent chain, substituent which is methyl carboxy, then cyclopropane carboxylic acid. Try these examples again. These are few examples so that if you want, you can revise them in detail in the previous topic of nomenclature where all functional groups are covered. Next is the preparation of carboxylic acids. First reaction, preparation from primary alcohol and carbonyl compounds. Some information already covered in the last chapter, alcohols. Like first information is primary alcohol and aldehyde when treated with KMnO4 or dichromate or Jones reagent, or you can simply say CrO3 in H+, or Tolling's reagent or Felling reagent or nitric acid, they give finally carboxylic acid. Primary alcohol and aldehyde group, that is important. Already we have covered in aldehyde ketones also this one, Tollens and Felling. In alcohols we have covered remaining reagents. Next information is ketones. Ketones when undergo vigorous oxidation. Here the term is vigorous oxidation with potassium permanganate or K2Cr2O7, then they oxidize. Otherwise ketones generally do not oxidize, but we can do the oxidation if ketone is, it all depends how the question is framed. If it is framed with alcohol, then you can go up to aldehyde or ketone. But any information is given like, or in the options given that on vigorous oxidation, what is the product form, then always consider that in the options they have given acid which is formed by the cleavage of ketone. So here on vigorous oxidation with dichromate, KMnO4 or Jones reagent, ketones give smaller carboxylic acid due to cleavage of the carbon bonds. Like in this example, both sides same arrangement, C2H5, C2H5. So from any of the side we can cleave bond like this. This part will give CH3COOH and this part gives CH3CH2COOH, like this one. Example second, here it is unsymmetrical ketone. Whenever unsymmetrical ketone is there, then majorly it will be cleaved from which side? Where more alkyl part is present, from that carbon we will cleave the bond, like here, or you can remember in that way, where smaller alkyl group is there, where smaller alkyl group is present, with that smaller alkyl group C double bond O retains. With smaller alkyl group, C double bond O retains and then bond is cleaved. This part will give CH3COOH, bond cleaved. This part will also give CH3COOH. Other possibility like this is also there, that bond cleaves in that way, but majorly if you go by the options, then always consider for unsymmetrical ketone, alkyl group retains with C double bond O and then bond is cleaved. This will give corresponding acids. Next reaction, from alkyl benzene also we can get COOH group. How? We use the reagents like KMnO4 or dichromates. Like here, condition, remember always one thing, that the benzyl carbon CH3 here, it should contain at least one hydrogen. One alpha H has to be there. Then complete carbon chain will finally gets oxidized to COOH. Like here, it contains 3 hydrogens, we want only 1. Therefore, finally it forms salt. Why? Because alkaline medium is given and then we acidify it to get COOH. Second example, benzyl carbon. Here it has 2 R groups but one benzyl hydrogen is present. This whole carbon chain will oxidize to carboxylic acid, firstly with KMnO4 OH minus heat, second with H plus. But in third example, this is benzylic carbon, it has no alpha hydrogen. This will not react in this reaction. If we take here styrene also, CH double bond C, it will also cleave the bond and get carboxylic acid. Now next reaction is hydrolysis of nitriles or amide groups. By hydrolyzing these functional groups, we can also get carboxylic acid. Firstly, nitrile group, when we do hydrolysis, acidic or basic medium, or acid catalyzed or base catalyzed hydrolysis, then firstly it converted to amide group, RCONH2, that we can say it is partial hydrolysis product. But generally the reaction will not stop here, and further this reaction goes till carboxylic acid. So remember, RCN with H plus H2O or OH minus H2O finally gives carboxylic acid. Amide is formed but reaction will not stop there. So in the question, if it is not mentioned, only given H plus H2O finally form carboxylic acid. If any hint is given like partial hydrolysis, then you can stop the reaction at amide or other reagent which I have mentioned here. You can go through it. In this example, RCNH plus H2O, what is formed? Carboxylic acid plus byproduct is there, NH4 plus. Here, nitrile with concentrated NaOH, this gives partial hydrolysis product there, which is RCONH2. Reaction will not proceed easily. So remember, if the term is partial hydrolysis, then we form amide, or if the term is concentrated NaOH, then also we form amide as the product. Otherwise, directly we go up to carboxylic acid. For example, benzonitrile H plus H2O. Finally, you go up to carboxylic acid. How? It will keep on adding there. H there, OH there, H, simple way. H there, OH there, H there, OH there. In short, if you add H on this one, nitrogen, and OH there from solution, this will take 2 OH. Single bond, this will get NH2. Ultimately, loss of water takes place and we get RCONH2. Then again, H there, OH there will form carboxylic. This is the easy way, but these reactions are very important and direct reactions. So better you remember nitrile to carboxylic directly. Here also, in this example, CH3CH2CN with concentrated NaOH or other term given, partial hydrolysis, then also CH3CH2CONH2 will be the product, that is partial hydrolysis product. Next reaction, from Grignard reagent we can prepare carboxylic. How? Remember, Grignard with CO2, carbon dioxide, R is having minus charge, and it will add on which carbon? It will add on CO2 carbon. It forms RC double bond OO minus, RCOO minus MgX. In dry iteration is there, solvent it is, and then we can acidify it, H plus H2O or H3O plus, it gives carboxylic acid. It is important reaction. Grignard with CO2 gives carboxylic group. Example, we take PHMgI. First step CO2 in dry ether, second H3O plus. We get PHCOO minus in first step, and after hydrolysis we get after acidification we get benzoic acid as the final product. Now next reaction is from acid halides, anhydrides and ester. We can prepare carboxylic group by hydrolyzing these groups. Acid halide with water or base catalyzed hydrolysis. Simply what we have to done here, we simply remove Cl or substitute Cl by OH group. It is, you can simply say it is nucleophilic acyl substitution. In simple language, Cl is substituted by nucleophile, which is OH there, here also OH. So finally, if hydrolysis is done, RCOCl or anhydride or esters, they give carboxylic acid along with other byproducts, like here Cl minus leave and OH is there from water. Same way here, alkaline medium, it forms RCOOH, but due to alkaline medium, that carboxylic acid will lose H plus and form salt. We can add H plus H2 and we get carboxylic acid. Simply nucleophilic acyl substitution, Cl substituted by nucleophile. Next, anhydride. Here also you simply understand that in anhydride group, that group substitutes by OH group RCOOH, and this O will take H plus, because if OH is coming there, H will go there. It is a simple way to understand the reaction. So RC double bond OOH and R dash C double bond O minus will take H plus, it forms carboxylic acid. Between these two, more important is acid chloride. Then esters also undergo similar type of substitution. This OR dash group, to better understand it, this will undergo substitution here. R dash O minus leave, it takes H plus and OH is there. What is formed? RCOOH plus R dash OH. In alkaline medium, OH minus H2O, again similar reaction, OH minus will substitute, it forms alcohol, carboxylate salt. Then we can add H plus, but here important point is that base catalyzed hydrolysis of ester is known as saponification. Base catalyzed hydrolysis of ester is known as saponification. Now here example, if we take this compound which is alkyl, that is methyl benzoate, on hydrolyzing ester H plus H2O, what is formed? Bond will cleave, it gives PHCOOH plus ROH, which is alcohol. Simply we are substituting Cl, substituting OCOR, substituting OR by the nucleophile. That's why nucleophilic acyl substitution reaction. Next reaction is by oxidation of alkene also we can get carboxylic. We can use strong oxidizing agents like KMnO4, we can use Jones reagent, we can use dichromate. This bond will be cleaved and this part will give R-COOH. Why? Because aldehydes are not stable when we have strong oxidizing agent, they further go for acid formation, and this part will give ketone. Now, if in the option they have not given any ketone, that means on vigorous oxidation that will also undergo further carboxylic acid formation. So remember, going through the options you have to select that which is more appropriate will be the answer. Generally, firstly we form carboxylic acid and ketone. On further vigorous oxidation, ketone will again give carboxylic acid. Now next reaction is from methyl ketones. We can also prepare carboxylic acid. This reaction, if you remember, in carbonyl compounds topic, it was haloform reaction, and then in haloform iodoform test. That is the reaction. We take example, here it is, we can take RCOCH3, or here it is, which one is it, acetophenone. First step with I2NaOH. We can also take Cl2NaOH, we can also take Br2, most commonly we take X2NaOH. Here I am taking I2 with NaOH. This first reaction is iodoform reaction. If you remember, that bond is cleaved finally, which gives Ci3 minus, and it forms PHCOOH. Then due to basic medium, COO minus is formed, and CI3 or CHI3 is formed, which is iodoform formation. So here we firstly form by this step PHCOO minus, that is salt of benzoic acid, plus CHI3. Then in second step acidification is done and it forms benzoic acid. So this is simply haloform reaction, and here I am taking I2, that is why here iodoform is formed, plus salt of benzoic acid form, then acidification is done and this salt becomes PHCOOH. Next reaction, this is again methyl ketone, bond will be cleaved in that way, and this part gives CHI3, this part gives finally carboxylic acid, which is C2H5 C double bond OOH plus CHI3, iodoform, that is yellow precipitate of iodoform is formed. Seventh reaction, oxidative ozonolysis of alkene. We can prepare by this reaction also. Here I am taking which alkene, which is containing CH, because if I take R group it gives ketone. So for relevant for us is acid formation. So here in this reaction, if you remember, in carbonyl compounds also done, and in hydrocarbons as well, ozonolysis bond cleave, it gives R-CHO, but in oxidative ozonolysis aldehyde further goes to carboxylic acid formation, therefore it forms R-COOH plus RCOOH. These are the two products formed by oxidative ozonolysis. We get carboxylic acid and ketone also possible, depending upon, if I write there R, this part gives ketone and this part gives acid. For example, in this case, bond is cleaving and left portion will give CH3COOH because it is oxidative ozonolysis, and right portion will give C2H5COOH. So these are the preparation of carboxylic acid. Now chemical reactions of carboxylic acids. First reaction, which involves bond cleavage between oxygen and hydrogen. When OH bond of carboxylic is cleaved, then which reaction? Acid base reactions. Although this type of reactions already you have done in acidic strength, here we are using that concept. Carboxylic acid with active metals like sodium, potassium, we can take zinc, we can take aluminium. So which bond is cleaved? This bond is cleaved, and H plus release, that H plus will take electrons from active metal, H2 gas evolved. That is also an indication that given compound contains acidic hydrogen, salt formed, H2 gas evolved. Second reaction with base, NaOH, carboxylic acid releases H plus, forms its salt plus water. Which reaction? Acid base reaction of carboxylic acid. Then next is third one with Grignard reagent. Now Grignard is here R dash, which is R minus will take H plus, alkane is formed, plus RCOO minus MgX plus. This reaction is used, third one is used to prepare alkane also. Fourth, sodium bicarbonate. This is very important reaction. Why? Because it is used as a test for carboxylic group, because when you go through the options you will find among them carboxylic acid will give sodium bicarbonate test. It is simply what? Acid base reaction. Stronger acid will displace weaker acid from its salt. It forms its salt, that means stronger acid will form its salt. Carbon dioxide is evolved, which is indication. CO2 evolved, that is the indication. Then next is with phenoxide ion. Stronger acid will displace weaker acid from its salt, forming its own salt, RCO minus Na plus generation of weak acid. Next reaction with NaCl. If it forms, then RCO minus plus HCl. Remember, stronger acid will not displace weaker acid from its salt. Here already salt of stronger acid, that's why weaker acid, that means carboxylic, will not displace stronger acid from its salt. Next one, similar to NaCl, this is already a salt of stronger acid, that means from RSO3H. Therefore, weaker acid will not displace stronger acid from its salt. This reaction is not feasible. Now next is the nucleophilic acyl substitution. Next reaction is nucleophilic acyl substitution, which is SN2TH mechanism, or no need to remember it, only for the sake of mentioning the mechanism I am writing SN2TH. Remember, important term is nucleophilic acyl substitution, and these are those reactions in which carbon and oxygen bond is cleaved, that is here shown in the part CO bond is cleaved. Previously in acid base OH bond is cleaved, here CO bond is cleaved. And in which category we are putting it? Nucleophilic acyl substitution. Now how it works? In short, what we are going to do? We are simply substituting OH group by nucleophile. How it is working mechanism? Nucleophile is there, C double bond O carbon. O will get minus charge, carbon becomes deficient. That means electrophilic center attacked by nucleophile. A tetrahedral intermediate is formed. That's why name is SN2TH, tetrahedral intermediate. And then again this minus charge quickly stabilizes, forming C double bond O, and OH leave. Here OH minus leaves. How? Because the electronic pressure is there, that's why quickly double bond O form. And in short, what we are getting in place of OH, we are getting finally a nucleophile, that is acid derivative nucleophilic acyl substitution. Now here what are the reactions possible? Important reactions: carboxylic acid with SOCl2 or PCl3 or PCl5. All these reagents you have done in alcohol. ROH to RCl. RCuCl formed plus SO2 plus HCl with SOCl2, or H3PO3 with PCl3, or POCl3 plus HCl with PCl5. Among them the best will be with SOCl2. Why? The byproducts are gaseous in nature. Second reaction we have done in alcohols again, which is Fischer esterification. What we are going to do? We substitute, although its mechanism is also done, but here I am not going through mechanism. Only important part we are going to do, we are going to complete it, that OH will be substituted by OR dash. This OH will be substituted by nucleophile, which is OR dash, and this is Fischer esterification. If you remember the points, we have done the points like as steric hindrance increases, rate of reaction decreases. Remember, and to increase the products, it is an equilibrium reaction. To increase the product side, we take excess of acid, or we keep on removing water, so that equilibrium shifts in the forward direction. The better is you revise from alcohols this reaction. Then third is with ammonia, OH leave. But here remember one thing: ammonia base and carboxylic is acid. It gives H plus 2 base, and what is formed? Salt, RCO minus NH4 plus. Then after heating, H2O releases and we get amide group. Remember, in this reaction, if ammonia heat is given, directly form RCONH2, and if ammonia is given, then it forms salt first. After heating, H2O is released. Next reaction, P2O5 or POCl3 or H2SO4, which are dehydrating agents. So we take how many moles? 2 moles of carboxylic acid, and from 2 moles simply H2O release, which is removal of water, that is anhydride formation, and we get acid anhydride group. These are the reactions in which COH bond is cleaved. Now next reaction is reduction using lithium aluminum hydride or diborane. It is or diborane or other reagents are also possible, but here we are only considering NCERT reagents. Lithium aluminum hydride, already we have done in alcohols also that lithium aluminum hydride is a strong reducing agent. It reduces almost all functional groups, does not reduce easily double bond, triple bond. In a particular cineamyl system, it reduces double bond. Generally, it reduces almost all functional groups. Now here we are specifically talking about carboxylic group. Carboxylic with lithium aluminum hydride in ether, and second step is hydrolysis. It finally gives alcohol. Reaction will not stop at aldehyde. If you remember, to stop at aldehyde stage we have used which reagents? PCC, Collins reagent, or other exact term in NCERT given is CrO3 in anhydrous medium, that reduces up to aldehyde stage. Another reagent which is clearly mentioned in NCERT as a better reagent as compared to lithium aluminum hydride. Why? Because if any other functional groups are present in the molecule apart from carboxylic group, then diborane will not reduce other functional groups. It reduces carboxylic acid preferentially. Reaction carboxylic group B2H6THF or BH3THF. Second step with acetic acid or H2O. It is overall hydroboration reduction. Then finally it goes up to alcohol. Right? Important point. This reagent will not reduce ester, nitro group, halo group like this. So better among them for reduction of carboxylic group is diborane. Next reaction is decarboxylation of acid. This reaction already covered in alkanes topic. Carboxylic acid with soda lime in 3:1 ratio, NaOH with CaO heat. Remember how to write the product. Substitute, in short, substitute COOH by hydrogen. What is formed? Alkane with one less carbon plus Na2CO3. Now if you remember in hydrocarbons alkanes, we have done this mechanism also. It's purely carb anion intermediate form, and more is the withdrawing group present, faster is the rate of decarboxylation. Fifth reaction again from alkanes, Kolbe's electrolysis. We can prepare alkane, alkene, alkyne by this method. So here it is alkane preparation, carboxylic acid 2 moles, NaOH electrolysis done. What is formed? Alkane, even numbered alkanes are formed plus carbon dioxide evolved. It is at anode. This reaction is done in your notes with mechanism in alkanes topic. So better if you have any doubt, you quickly revise that notes. Plus H2 gas evolved and OH minus 2 moles at cathode. Remember what are the products formed at anode and what are formed at cathode. CO2 evolved at anode and H2 evolved at cathode. Now next reaction is heating effect on dicarboxylic acid. These are some important examples. If we take O, here is oxalic acid. Oxalic acid on heating evolve 1 CO2 giving formic acid. We can heat it further, which gives carbon monoxide, but with no CH2 in between, dicarboxylic acid, which is oxalic, right? We'll use this point. I'll tell you how. Firstly, there is no CH2 between, so we can say it is 0. It is oxalic acid. With oxalic acid, 1 CO2 evolve. Second, with 1 CH2 in between these two carboxylic group, this is the particular acid which is malonic acid. In malonic acid, again 1 CO2 evolve, and it gives CO2 evolve and gives CH3COH. Second reaction is important. It is geminal dicarboxylic acid. Direct heating evolve 1 CO2 and we get carboxylic acid. Here it is CH3COOH. So see, in first one, when there is no CH2 between two COOH groups, CO2 is evolved. Second case, when there is one CH2 between two carboxylic groups, again one CO2 is evolved. So when 0, 1 case is there, evolve or remove one CO2 and write down the product. Third one, there are two CH2 groups between dicarboxylic groups. This is succinic acid. when there are 2 or 3 CH2 groups, then H2O is evolved and it gives a stable cyclic product. When H2O is evolved, it gives this type of evolve and it gives C double bond O, C double bond O and one oxygen in between, that is anhydride is formed. Then how many carbons? 3. With 2 and 3 carbon in between 2 COOH groups, what is evolved? Water with 0, 1 CO2. After 4 and so on, both CO2 and H2O are evolved. So in next case, which is glutaric acid, on heating, again 1 H2O evolved and we get C double bond O, C double bond O, in between one oxygen. This is heating effect. It is important sometimes. This is used in between the multi-step reaction. Okay. So remember 0, 1, 1 CO2 evolved, 2, 3, 1 H2O evolved, and so on, both CO2, H2O evolved. But that is not much useful. Initial are useful. Oxalic, malonic are more useful. Succinic is also useful. Next reaction is Hell-Bollard-Zelinsky, that is HVZ reaction. It is important name reaction of this chapter, which is basically alpha halogenation. So now in this case, carboxylic group, this is alpha position with red phosphorus and X2, that can be Br2, that can be Cl2, and second at the end we do hydrolysis adding water. It gives at alpha position one halogen is substituted. It is electrophilic substitution reaction, and if we take excess of reagent, then all the alpha hydrogens will be substituted by halogen. So easy way is carboxylic group, red phosphorus with halogen, and then second step is with water. We do at alpha position halogenation, and if excess or multiple times it is given, then all alpha H will be substituted by halogen. For example, in this case, P plus Br2 and H2O. Now, which is alpha position? This is alpha position. At this, halogenation takes place Br. And then we can do further other reaction, alcoholic KOH heat, which is dehydrohalogenation. That means beta elimination. Then alpha carbon, leaving group depart, beta carbon, hydrogen, and this gives alkene as the product. So this is HVZ reaction, which is also very important. Next is electrophilic aromatic substitution reaction of COOH group on the benzene, that is benzoic acid. Now if you remember, carboxylic acid is deactivating group because it's minus M, it is minus M as well as minus I. So here deactivating group, and it is meta directing. So first reaction, nitration. Nitration NO2 plus electrophile, it will go at which position? Meta position. Why? Because here COOH group is meta directing because it is deactivating. Second is bromination, Br plus is electrophile, Br plus will go on the meta position. Now important point here is benzoic acid will not participate in Friedel-Crafts reaction. This is important point because which groups are not participating? If you remember, phenol will not participate, NH2 will not participate, carboxylic acid, that means benzoic acid, will not participate in Friedel-Crafts reaction because it deactivates and it reacts with the Lewis acid catalyst as well, due to which it becomes strong deactivating, and that's why it is not participating. The important point is it is not participating in Friedel-Crafts reaction. Then next are the some reactions of acid derivatives, like which groups are C double bond O G. That group can be halogen, that means acid halide. That group can be OCOR, that means acid anhydride. That group can be OR, that means ester. That group can be NH2, that means acid amide. So these are the acid or carboxylic acid derivatives. Now, what is their general reaction? We have done recently nucleophilic acyl substitution. That group will be substituted by nucleophile. That is the simple way to understand it. That group will be substituted by nucleophile. Now here, the reactivity order towards nucleophilic acyl substitution. fastest for acid halide, then acid anhydride, then ester, and then amide. This we can easily explain that here halogen dominating effect is withdrawing, which is -I. This makes the carbon more deficient, faster in the substitution, faster attack of nucleophile. Then OCOR plus M dominates, OR plus M dominates, NH2 plus M dominates. Among these three groups, it has weakest plus M. That's why it is faster in the attack of nucleophile. Or if you go by other way, that leaving group ability, X minus is better leaving group than others. This is better leaving group than other. Why? Because this negative is in conjugation further. Between these two, NH2 is weakest leaving group. Why? It is strongest base. So you can go by any other way, but reasons are generally not asked. Reactivity orders are important. Acid halide maximum, acid amide least in nucleophilic acyl substitution. Now here are the some general reactions which are related to acid halide. Like first one, acid halide with H2O. Nucleophile will substitute Cl. What is formed? RC double bond O OH. Next is alcohol. Cl will be substituted by OR dash, ester is formed. With NH3, finally Cl leave, NH3 will attack, and finally we get RCO NH2. With Grignard, it is important reaction. Grignard CH3 acts as nucleophile. Cl minus leave, CH3 attack, we get ketone. Remember, if Grignard is in excess, the reaction will not stop there. Grignard will further attack and goes up to, remember, tertiary alcohol. So here I am only writing that yes, to remember, firstly substitution and then addition takes place, which is useful for alcohol. Then after these four reactions, this is fifth reaction. They are not linked. This is acid halide with catalytic hydrogenation. It gives alcohol or reduction. Next one is diol H, diisobutyl aluminium hydride. It is important reagent because this reagent also reduces up to aldehyde, RCOCl2, RCHO. Even it will reduce RCN, that is nitrile, to RCHO, or ester group to RCHO. That's why diol is also important reducing agent. It is selective reducing agent. Then H2 with PDBSO4. If you remember this one, in aldehyde ketones we have done Rosenmund reduction. RCOCl with Rosenmund reduction, that is Lindlar's catalyst, gives RCHO. With lithium aluminum hydride, this also gives alcohol, RCH2OH. Then next reaction, RCOCl, acid halide with benzene in anhydrous AlCl3. It is Friedel-Crafts acylation reaction. This generates acylium ion, which is electrophile and undergoes electrophilic aromatic substitution, and we get carbonyl compound, that is RC double bond O benzene. Next reaction, dialkyl cadmium. In carbonyl compounds we have done that reaction. This is better in comparison to Grignard. Why? Because it is less reactive and reaction stops at ketone. So among that, one R will substitute one Cl and we get RC double bond O R dash, or we can write twice there. Okay, these are some reactions for RCOCl. Now next are some general reactions related to which group? Ester group, RC double bond O R dash. Now in this case, first reaction, H plus H2O, simply it is like RC double bond OG. G group is substituted by OH. That's like nucleophilic acyl substitution. Group substituted by nucleophile, and what is the intermediate formed? A tetrahedral intermediate formed. But you remember direct reactions, no, for better understanding we have done SN2TH reaction, nucleophilic acyl substitution. But most important is how to write the product. That group is substituted by nucleophile. That means OH there, and this R dash O will take hydrogen, becomes R dash OH. This is simply hydrolysis, acidic hydrolysis of ester. Second is again similar reaction, but it is base catalyzed. OR dash substituted by OH, carboxylate salt. Why? Because it is alkaline medium, plus R dash OH. Now basic hydrolysis or base catalyzed hydrolysis of ester is known as saponification. Next is ester with alcohol, any other. Here I am writing CH3OH. We can take any alcohol in acidic medium. This is an important reaction. OCH3 will substitute this OR dash. Why? Because here it is acting as nucleophile. What is product? Again an ester is formed. That's why this is transesterification. Means ester with another alcohol, the ester OR will substituted by alcohol and again a new ester is formed, and that is transesterification. Fourth reaction is reduction of ester group. It simply cleaves the bond like this and RCH2OH R dash OH is formed. Grignard reagent, if we treat with one equivalent, firstly substitution, nucleophilic substitution, OR dash substituted by CH3, then ketone is formed, and then if we have further more equivalents of Grignard, CH3 MgBr, then this will be nucleophilic addition on carbonyl compound O minus, CH3 will add over there, O minus will take H plus, and reaction will go up to tertiary alcohol. Then next is useful for amide, that if we take succinic acid with NH3, it firstly forms salt. Now remember, this reaction is important because of given in NCERT also. Heating is given, then remove H2O. H2O release, what is formed? Amide formed. Then further strong heating around 200 degrees Celsius. Then what is evolved? It releases one NH3, one ammonia molecule, and we get succinamide formation. Okay, this is important reaction. If we take simply carboxylic acid RCOH, it forms RCONH4. Heating, H2 release, amide is formed. But here it is dicarboxylic, diamide formed, and then strong heating term should be given. Strong heating term should be given. Then 1 mole of NH3 is evolved, resulting into amide, succinamide formation. Okay. Now next is phthalic acid. Phthalic acid with ammonia. Firstly it forms salt, and I have written already heating. That means it releases water and then forms amide, CONH2, CONH2. Then in this diamide, strong heating term is written. That means out of these two, one will evolve as NH3 and we get this product which is phthalimide formation. Just like in last example we have done succinamide formation. Important examples are these. Then some reactions of amide. Amide with lithium aluminum hydride undergoes reduction. Remember, C double bond O of amide is reduced to CH2. Remaining all C double bond O is reduced to alcohol. But in amide, after lithium aluminum hydride, it forms RCH2NH2. That is primary amine formed. Second reaction is if you remember P2O5 or POCl3 or SOCl2, they all are dehydrating agents. H2O evolve and we get nitrile as the product. That is RCN formed. Why? This is dehydrating agent. We can use POCl3 heat or SOCl2 heat, or other reagents are possible, but most common reagents I am telling you. Then next reaction is very important reaction. In amines chapter you will do that one. This is Hofmann bromamide degradation. In this reaction we get primary amine. Important part, it is in the preparation of primary amine. Then we get primary amine with one less carbon, that is C double bond O, remove, and RNH2 combine. That is the fast way to write the product, but in actual a proper mechanism is there which is not that useful, but if you have time then go through that part. Important part is, remember, amide with Br2 KOH or KOBr gives primary amine with one less carbon. Byproducts are important, K2CO3 formed, KBrS2O. In NCERT balanced equation is given, so remember the balanced equation. Another important question can be the CO finally goes to carbonate. CO of amide finally goes to carbonate. Then next are some other reactions like NaNO2 HCl, NH2 group substituted by OH group, H2 evolved. Last reaction is hydrolysis. We may take acidic medium or basic medium. Amides on hydrolysis finally gives carboxylic acid. and byproducts are there. So these are the reactions of acid derivatives.